Welcome everyone. This is our 13th Q webinar under QWorld. We started last May, and before May, we already have our 13 Q webinar. Today we will have Cem Say. First, I would like to thank to him to accept our invitation. He is also a very special guest of QWorld. I will shortly mention. So today I and Özlem will moderate this Q webinar. Let me start first our code of conduct and protocol. In QWorld's activities, we always have some codes. So we are here to talk about quantum science education, and then let's stick to this plan. And we are already recording this meeting, and it will be available later from YouTube channel. And please don't record it or don't distribute it because you didn't ask permission of participants. And also, you can ask your questions by commenting us on YouTube or in Zoom. We will collect them, we will observe them, and at the end, we will ask to Cem. So I will do also two short announcements. We are very happy that now we have a complete set of introductory material on quantum computing and programming. Maybe some of you already know, we had a previous material tutorial called Bronze. It has already been organized more than 50 times in different parts of the world. Now, as a continuation of it, we have now second material. It is Silver. It's already been organized as a pilot workshop internally under QWorld, and we will open to globally after a few weeks. So we welcome you to apply for this let's say first global workshop. I will also share the link in the comments soon. And this time we will focus on the exactly Shor's algorithm. So you can just get some pedagogical introduction today. And after a few weeks, you can also go through our material Silver. This summer, we also have our first, let's say, we did also last summer internally, QIntern 2020. It's our online internship program. It was a success last year, and we are repeating this for this year. We are also welcome the mentors and also interns. I will also share a link about it in the comment. Currently, we are collecting the projects from the mentors. And in June, start from beginning of June, we will announce the projects and also we collect application from the interns. So today we have Cem Say. We are very proud of also to have him because he was my PhD advisor. He was also PhD advisor of Özlem. 2 years ago, when we forming QWorld first time, we also form a management board, and there were 7 people. We call it QWorld. Indeed, 3 people from this board, academically children of the Cem Say. One is me, the other is Özlem, also my PhD student. He's academically grandson of Cem Say. He was also there. So almost 50% of the first QWorld formed by the, let's say, children and grandchildren of the Cem Say. He's from Turkey. He is very well known with his popular science on artificial intelligence, on information theory, and some other topics. He started his career as a artificial intelligence topic. Later, he showed an interest to theoretical computer science and then quantum computing. And with his students, such as me and Özlem, he go through automata theory, complexity theory, and the quantum computing. So now I will give a stage to Cem Say. Thanks again inviting for this talk. And I believe that it will be one of the best introductory lecture for the Shor's algorithm. Yes.
You think so? Okay, thank you very much for the invitation, and I'm very happy to be here, like as always, sitting in my home, but also among you virtually. And I'm very, very proud of what QWorld is doing because of the, you know, being its like partial ancestor and so on, as you mentioned. I congratulate you all on what you have been doing. And today I'll talk a little bit about factorization and Shor's algorithm. So let me try to share it. So I hope you see my screen. Now, okay, Shor is the famous Peter Shor, who invented the quantum algorithm for factorization. And you see two very nice photos of him, an earlier photo and a later photo. But he is laughing in both of them. That's what's important. So I think Shor's algorithm is a masterpiece. It's like a fascinating algorithm, and whenever you teach it in the quantum computing course, you get really fascinated by it. I mean, how could one person know so many things and connect them together to form such a masterpiece? In addition to like inventing things that nobody knew about earlier, you also have to know a lot of things that like many people normally don't know. Okay, so it's really a masterpiece. I think he should get a Nobel Prize, I guess in physics, right? But anyway, so this is my message to the Nobel Prize Committee. But anyway, let's start. I'll first talk about what factorization is, why we think it's an important problem, and so on. What has been done about it until Shor, and then what Shor did. Right, that's the basic story that I'm attempting to cover here in a quite introductory way. Doesn't require any complicated knowledge of mathematics or physics or whatever. All right, let's start. I think this is a page from Euclid's Elements, you know, that famous mathematics textbook, which was written 2,300 years ago by the famous Euclid of Alexandria, I believe. And the problems that we are talking about here, the basic concepts that we are talking about here now, were already there, and Euclid made some of the contributions which later formed like parts of these modern algorithms, including Shor's algorithm. So this is really a very, very old problem that mathematicians have been thinking about for a really long time. Anyway, so like and this book, Euclid's Elements, was really a standard mathematics textbook for about 2,000 years. I think until the 20th century, everybody like was required to read this in order to become a well-educated citizen. Anyway, so the basic concepts that were already known back at that time are the following. Every natural number, every integer greater than 1 is the product of one or more primes, right? Every such natural number is either itself a prime, or it is a composite number, which is like it is obtained by multiplying maybe a prime with itself or with some other primes. All right. So like the primes are like the atoms of all the numbers. They are doing the real job of producing the other numbers, if you see what I mean. And among other things, okay, Euclid knew all about those things and so on. And one thing he provides in this book is a fast algorithm for finding the greatest common divisor of two numbers, which if you are a computer engineer or even a student of something like that, you probably have already seen, right? So there is a really easy, brilliant, but easy, fast algorithm for computing this. I give you two numbers and you find their greatest common factor, right? So this is easy. But the following problem is not so easy. And this is the factorization problem. I give you a single number and I ask you to find its factors. It's the primes making it up, right? I give you a number and I ask you, really, please tell me which primes are multiplied in order to obtain this number, all right? So in this particular case, the answer is easy. 3 times 5 is 15. However, if the number is kind of a bigger number, the longer number, because I'm interested in the number of digits making up the number. So I may be talking about the lengths of numbers, and that's what I mean in this presentation. Anyway, as the number gets larger, the problem sort of becomes more difficult, right? I mean, can you see this obviously? It is 13 times 17 times 243, but like normal people like us cannot see this obviously. And okay, is there a good way of finding this out quickly? That's the question. This is factorization. Given a number, find its factors. So why is this problem an interesting problem to many people, including like people who are not directly interested in the beauties of mathematics? Okay, well, essentially, this is the computation going on here is of a form that, like, if you think of the inverse of this computation, if you think of this in the other direction, this seems to be an easy thing to do. What do I mean? I mean, if I gave you the three numbers that we saw before, 13 times 17 times 243, and I ask you, you know, what is the product of this? Okay. I mean, you already know like a fast algorithm from primary school, which helps you multiply integers. So like, this is like the inverse of multiplication, right? And multiplication is easy. We know a fast algorithm for it. So why is it difficult in the other direction? All right. Right. I mean, isn't this exciting? If this, like, just this question doesn't excite you enough, this is connected to lots of practical issues. In the 20th century, people like thought about this a lot, and they said that, hey, this problem is of this nature, right? Computing it in one direction is easy, and computing it in the other direction seems to be difficult. And such functions can be used for cryptography. They are used actually in the cryptographic protocol that lots of cryptographic protocols that are supposed to secure our communication with our online bank, or secure our credit card information when we are communicating with an online vendor and so on, right? This kind of thing can be used to make the job of people who don't have the password difficult. On the other hand, people who have the password can easily do the thing that is supposed to be done. This kind of function is good for building such cryptographic systems. And like the one that I'm talking about, the most famous one of those systems is based the RSA protocol. You have heard of it. And these letters come from the names of these three mathematicians, Ribest, Shamir, and Edelman, who did this wonderful mathematical reasoning and gave us this protocol that is currently still being used to secure lots and lots of important information. So this whole thing is based on the assumption that factorization is difficult. Okay, and what do we mean by difficult in computer science? Actually, theoretical computer science seems to be like, I mean, if you want me to explain to you what theoretical computer science, or like a major subfield of theoretical computer science, complexity theory, is in one sentence, it is the science of understanding what is difficult and what is easy. All right, so our technical understanding of the word difficult is as follows. Okay, we are talking about algorithms that can like do some job, and we expect the following things from an algorithm. First of all, it should be efficient, right? It should run in a reasonable amount of time. For instance, you already know an algorithm for factorization, right? Probably you did this in primary school or something like that. I mean, somebody gives you a number, and really there is an algorithm that they teach you at that very early age that helps you to find the factors of that number. It just goes through, you know, let me try to divide the number by 2. If it nicely divides, then 2 is a factor. Otherwise, let me try to divide it by 3. Let me try to divide it by 5, and so on. So like go through all possible primes and do trial divisions. But what you see, although that algorithm finally works, it lets you find the factorization. It doesn't run in a reasonable amount of time. It takes a huge amount of time. And in complexity theory, we have a way of like measuring that speed of algorithms in that sense. So a good algorithm that we are looking for should be an efficient algorithm, a quick algorithm in that sense. And of course, I mean, this goes without saying, the algorithm should give the correct answer. I mean, otherwise, I mean, it doesn't earn the right to be called an algorithm, and it should give the correct answer, preferably like always. I mean, every time you give a question to it, it should run a short amount of time, and it should give you the correct answer. But in some cases, we also allow probabilistic algorithms where, okay, maybe it doesn't give you the correct answer all the time, but like it has a theoretical guarantee that the answer that it gives to any question will be correct with, I don't know, with 99% probability, something like this, with great probability. And this happens when, you know, you allow your algorithm to use some randomness. Amazingly, it seems that allowing algorithms to use randomness sometimes increases, or it seems to increase their power to do things. Anyway, and of course, you know, for mathematicians, this is very important. These things, the things that I've already said, these good things, that good properties that your algorithm possesses, they should be proven, right? Somebody shouldn't just claim that his algorithm has all those properties. He should prove them. He should provide a mathematical proof to you that it really has all those properties. All right, because we will see, for instance, now some algorithms which don't have that property, right? Okay, but ideally, an algorithm should be like this. Well, in that sense, factorization has been difficult for a very, very long time. Okay. So the fastest known classical algorithm for factorization, by classical algorithm, I mean like an algorithm that is running on classical computers, not quantum computers. I mean, before Shor came along, okay, didn't have these properties, like most of these properties, okay? So now this is the scientific paper, the abstract of the scientific paper, which announced that fastest known classical algorithm for factorization. And if you like look at the bottom lines, the third line from the bottom of this algorithm, it says that essentially it runs in exponential time, exponential e to the power number of digits, cube root of the number of digits, right? In the input, that is the runtime they think that the algorithm requires. So I'm saying that this seems to run in exponential time because they haven't rigorously analyzed it. This algorithm, right, doesn't have that kind of proofs about its runtime or even its termination properties, I guess, even guarantee that it will terminate. It's not that kind of algorithm. It's like lots of heuristics are going on there. Anyway, this like currently best classical algorithm for factorization takes a lot of time. It's exponential time means this algorithm takes like too much time. Okay, and we would like our algorithms to be polynomial time algorithms. So the runtime of the algorithm should grow as a polynomial function of the length of the characters in the input, the digits of the number that we input. That's what we are looking for. That's what we want from an algorithm's running time. Okay. And, you know, we don't have such a classical algorithm known for factorization yet. You may have heard of the famous P versus NP problem, the $1 million problem in theoretical computer science about, talking about exactly those things, which problems are difficult and which problems are easy and so on. So in the unlikely case that P equals NP, the answer to the P versus NP problem is yes, then factorization should be easy. Factorization should have a quick classical algorithm. However, nobody knows if P equals NP or not, and certainly nobody knows of a quick classical algorithm for factorization. On the other hand, if, as people suspect, P does not equal NP, if the answer to that famous unanswered problem is no, this still doesn't settle the question of factorization. So like, we really don't know whether there is a fast classical algorithm for factorization or not, but we are, kind of sure that we don't know such a classical fast algorithm for factorization. And if you are interested in these things, there is a famous list of like seemingly difficult problems called NP-complete problems in the theory of computer science. And factorization is not one of those problems. I mean, this makes its status even more mysterious, right? Anyway, let us analyze the difficulty of factorization a little bit further, because in some cases, for some numbers, factorization is easy. All right, I give you a number, and you can like easily tell me its factors in some special cases. So let's go through those special cases a little bit. For instance, if the number that I give to you is even, if its last digit, least significant digit is 0, or if you are doing this in decimal, if its last digit is 2 or something, you can easily see if a number is even or not by looking at its last digit, then boom, you have already found a factor. 2 is a factor, right? So like, I wish the world was like that, but not all numbers are like that. In slightly more complicated case, but still, if you know of programming and so on, if you think about like 2 hours on this problem, you will see that if the number that we want to factorize, we are given, is of this form, I mean, it is the power of some other number for 2 integers C and D. These things are called perfect powers. Then you can determine whether the number that you have been given is a perfect power or not. And if so, of course, C is clearly a factor. In a short amount of time, there is a really I think a few 100 years old algorithm, I think so, for solving this. But of course, you may not be so easy and may not be a perfect power. And if n is itself a prime, I mean, if I give you a number, if there was a way of understanding whether the number is itself a prime number or not easily, then, and it turned out to be a prime number, then that would be another easy way of finding whether finding all the factors of it, because like then in that case it only has one factor itself. All right, now this was a mystery, this was a difficult question until about 1975, and in 1975 people finally understood that we can now really understand quickly whether a given number is prime or not. The algorithm that you learned in primary school is once again not quick, and essentially, Gary Miller invented an algorithm, a quick algorithm, a polynomial time algorithm for determining whether a given number is prime or not. However, who is the guy with the older picture? That is the famous Riemann from the 19th century, famous mathematician Riemann. Well, Miller's algorithm is quick only if something called the generalized Riemann hypothesis about some deep facts about prime numbers is true. So there is this famous Riemann hypothesis, and then like I think some decades after Riemann died, somebody like even made a more general hypothesis built on Riemann's hypothesis, and mathematicians think that it is true, but it has not been proven or disproven yet. So if that thing, which is thought to be true, is true, then Miller's algorithm is a polynomial time quick algorithm for determining whether a number is prime or not. Okay. However, I mean, this need for Riemann to be true was eliminated 25 years later by these three Indian scientists, Agrawal, Kayal, and Saxena, when they finally invented an algorithm which can quickly determine whether a number is prime or not, without requiring any unproven hypothesis to be assumed. Okay, so in these cases, factorization is easy. But what if the number that you are given does not have these nice properties? Then factorization is like difficult, right? Okay, and the numbers that those cryptographers use are carefully selected so that they don't have these properties. They can't be factorized easily, all right, by these easy algorithms. Well, so until the 1990s, the situation was this, all right? We knew how to factorize n if n had one of these nice properties, but we didn't know what to do after that. If n didn't have any of these nice properties. And then Peter Shor came along. All right, so now the story of Peter Shor is about to start. Okay, so how did he handle the rest? How did he handle these difficult cases? Well, an important piece of mathematical information that Peter Shor knew about is that factorizing a number is as easy as solving the problem of order finding. What is order finding, you would ask? And the question is, the definition of order is this, okay, in the context of our talk. If somebody gives you two numbers, a and n, the smallest number r, such that a to the power r is congruent to 1 modulo n, meaning if you divide it by n, the remainder is 1. The smallest positive number r, which has this property, is said to be the order of a mod n. So if somebody gives you two integers, a and r, a and n, and r is defined from them according to this, this description that you see now. All right. So, and it is known once again since the 1970s that if you have a quick procedure that can find the order of a mod n, if you have a quick algorithm for doing this, then by, just by calling it a few times and doing some multiplications and so on, you can factorize the number n quickly, okay? Just randomly select a few a's, find the order of a mod n, and then hope to some extra easy operations let you factorize, find the factor of n quickly. And who invented this? Once again, Miller invented this. I think once again, assuming Riemann, all right? But if you just allow yourself to use some randomness, then even without assuming Riemann, this link between the problems exists. All right. So people knew since the 1970s that the factorization problem would be solved if somebody found an algorithm for doing this, for order finding, right? And who invented that algorithm? Peter Shor invented that algorithm. That's the contribution of Peter Shor to this randomization puzzle, right? That's what he invented. Because if you are able to do this, then the rest of the problem of factorization is solved by virtue of things that people had already discovered. All right, so how did Shor go about doing this? He had to use a quantum computer to do this, because we still don't know how to solve the order finding problem quickly using classical computers. So, but Shor knew about like the ideas about quantum computers and so on, and he saw that, oh my God, I can apply these. If I only had a quantum computer, I would be able to solve order finding. So Very quick update on quantum. Of course, like as people who are watching this, you already are familiar with most of these ideas. But anyway, so quantum world, the quantum world is strange, but the scientists tell us that all this strangeness is true. All right, so it seems that in the world of quantum, like those little particles can be in many places at the same time. One thing can be in like two places at the same time, or one object can be in more than one state at the same time. Or some people like to think of this as there are many parallel branches of the universe, each containing that single thing in different places, or that single object in different states. This is like one way of understanding what quantum equations seem to be telling us. And a quantum coin flip, a way of setting a little quantum system into a certain strange state, superposition state, can be easily described so that a quantum bit, a qubit as they call them, can be in a both 0 and 1 state, simultaneously. And if you have like 1,000 of those qubits side by side, then their composed state, would be in one of 2 to the 1,000 different possibilities, if you think about it. And if you are favoring that interpretation of quantum mechanics, then like that system would be existing in 2 to the 1,000 parallel branches, in each of them containing a different state of that amount of memory simultaneously. All right. And parallel copies of the same thing can be made to interact among themselves using, mirrors and electron things that physicists know better about. And sometimes those parallel copies of the same thing can be made to cancel each other out and reinforce some other possibilities. This is something that like doesn't have a counterpart in for classical computation, although it has a counterpart if you think about what waves are doing in the sea and so on. And this parallelism of quantum system being in more than one state and at the same time goes on, physicists tell us, until somebody like opens the box and looks at the system. When you look at it, when you observe it, when you interact with it, the story goes, you see only one of the values in the superposition. I mean, you don't see the cat, as they say, both dead and alive. You see it either dead or 100% dead or 100% alive. And which one? This is randomly selected by nature. So a way of interpreting this whole thing is, as I told you, to think of like parallel worlds existing side by side. And when you do the observation, another copy of you in a parallel world is observing the cat to be dead and becoming sad. On the other hand, in this world, you are observing the cat to be alive and you are happy. All right. So, and the famous physicist David Deutsch, you have to follow him on Twitter, is one of the people who is most excited about that way of interpreting quantum physics. Anyway, and if you build computers based on these ideas, these interesting features of little particles, then your computers will be more powerful, it seems, than our classical computers. That's the whole deal. So now let's seriously, examine how Shor's algorithm works. Shor's algorithm is for order finding, as I already mentioned, right? So it is really taking two numbers as input, a and n, and its aim is to find the smallest number r such that a to the power r is congruent to 1 modulo n. If you divide a to the power r by n, the remainder is 1. It's looking for the r, smallest r, which makes that thing over there true. Because as I told you, if you had a quick way of doing it, then like you can plug it into an already prepared algorithm, which was waiting for like 20 years, hop, and then you would have a quick algorithm for factorization. So all that was needed was an algorithm which does this thing quickly. And Shor's algorithm, as I will try to show you, does this with reasonably high probability. So I'm not claiming that like the moment you press the button, I mean, in its first execution, Shor's algorithm gives you the correct order R with 100% probability. No, I'm just claiming that it does it with some reasonable probability. All right. So this concept may be interesting. I mean, how can this work? I mean, if it has only a chance of giving the correct answer, like with 10% probability, how can I call this a good algorithm? People ask, but you know, you will see that this is enough as long as it's some constant probability of like being correct for every question that is asked to it. This works. This works because we can just, look at the overall result of the procedure. You know, the overall procedure is supposed to find a factor for the number n, right? So you just run the algorithm assuming that the Shor subroutine's answer was correct, and you know, the algorithm ends and it gives you some result, and then you can check whether the output of your algorithm, your factorization algorithm, is really a factor of n or not. You checking this answer is easy. You just divide the number that you get as output of your algorithm. You divide n by that number, right? So if it's a factor or not can be determined really very easily. And so, like, if the first execution of Shor has given you like a wrong answer, never worry, do it again. You know, run it again, and it will give you an answer again, and then attempt to factorize using that again. Now, since it has a constant probability of giving you the correct result, some constant positive probability of giving you the correct result, it can easily be seen that like a constant amount of runs later, really, you will get your factor. Okay, this is the nice thing about such algorithms called Las Vegas algorithms in computer science. Shor's algorithm is a Las Vegas algorithm, as they say. Anyway, so how does it work? I mean, of course, I can't give you all the details. I mean, last time I tried to explain Shor's algorithm in my quantum algorithms course, we really went slowly through it, and it took about a month, right? So we don't have that kind of time now. But anyway, the basics are the following. It's essentially composed of 4 stages, Shor's algorithm. You start by creating a huge number of parallel branches, the kind of branches that I was mentioning, right? When we were talking about this quantum computation. Although maybe we can come back to it and ask a minute later whether this same thing couldn't be done in classical computation. Anyway, so it starts with creating a huge number of parallel branches. I'll be talking about it in a slightly more detail like a minute later. After that, it does something called some little well-known kind of computation called modular exponentiation. What this is, I will explain. It's really a fancy name for a not very difficult calculation. All right. And then it does the really genius part of Shor's algorithm, a computation called the quantum Fourier transform, which we will be talking about a little bit. All right. So this is the end of the 3rd stage. And these 3 stages are happening in really on your quantum computer, right? And then there is a classical post-processing stage in which from the output of the 3rd stage, you do some extra things, essentially things which were like really known like thousands of years ago. Anyway, you do some extra work and finally find the order. All right. So if you have a quantum computer, you can run this algorithm, details coming soon, and find the order of A mod n with high probability. So now let's not be timid and let's look at the details. What is Shor doing when he gets two numbers, A and N? First of all, he decides how many quantum bits he will be using. For a technical reason that only becomes apparent, its reason only becomes apparent at the very end, in the end of the last stage of the algorithm. You have to prepare a quantum memory device which is somewhat bigger than what would be required to write the number n in. Okay? So, I mean, if n requires some number of bits to be written, your device should be somewhat bigger than, like 10 times bigger than. All right? So it's not dramatically bigger. The number that can be written using that many extra bits is dramatically bigger than the number that can be written using only number of bits required to write n. So you have some quantum memory device, and you initialize all the quantum bits that you have in it to 0. No big deal. Currently everything looks like a normal classical algorithm would look like. Now you do some quantum thing on your bits, which I mentioned earlier, right? You perform an operation on each of your bits so that each of your bits becomes with 50% probability, I'm inclined to say 0, and 50% probability 1, all right? So if all of your bits are in this state, then the combination, the whole register containing all the bits is now containing, if you think about it in this way, with equal probability, all numbers from 0 to m, all right? And how are you doing this quantum coin flip? If you are familiar with what Abuzer and people in QWorld have been doing, there is this elementary quantum operation that we are very fond of, called the Hadamard gate. And it's a little computation which takes a qubit in the 0 state, and boom, after the Hadamard gate is executed, your qubit is now like half 0, half 1. All right? The 1/√2s correspond to things we call amplitudes, like the weights of 0 and 1. And the square root shouldn't intimidate anybody, because in order to calculate the probability that somebody would observe, whether he would observe 0 or 1 when he looked at it, you take the square of this number. All right, so that Hadamard gate is like the first thing that people learn when they start studying quantum computation. So that's the thing that you do to your qubits at the beginning of Shor's algorithm. So not very dramatic up to now. So as a result of this, now your memory device is in a superposition of all numbers that can be written using that many bits, all numbers from 0 to m. Now let's think about it a little bit. What really is the situation in my memory device right now? I don't want to observe it right now, because as I told you, when you observe a quantum system, it's like magic disappears and so on. But if I observed it right now, I would have an equal chance of seeing any number from 0 to m, right? Because like all numbers, all possible numbers from 0 to m are now existing with like an equally small probability, like sort of on top of each other or in parallel worlds, if you like that kind of thing, now in this machine. All right, so if I observed it now, I would see by some, natural lottery, with equal probability, one of those numbers. If somebody could list those numbers, that list would look like all the numbers from 0, 1, 2, 3, up to m, I think up to m minus 1. All right? I am saying if somebody could list them, because it would be impossible to list them, because m is a very, very big number, if you think about it, right? That's the whole thing. We are given a big number and, you know, n, and m is like a considerably bigger number than that. And like, we don't have the energy, we don't have the space or anything to actually write this list anywhere. But through the magic of quantum, those numbers are like superposed now in our memory device, so that if I observe them, if I observed my memory device right now, I would see with equal probability one of them. Okay, but currently I'm not observing them. This is just the prelude to the exciting things that we will be doing. Okay. Anyway, so this is the end of part one. So the modular exponentiation part of Shor's algorithm is beginning. Remember, currently I have a number in my memory. If you are viewing this quantum thing according to the parallel worlds interpretation, I guess, you know, one copy of me in this universe has a number in his memory device, and another exact copy of me in the parallel universe has another number in his memory device. Like, there are like m copies of myself in m parallel universes, and everybody has a different number in his device. I think that's the way David Deutsch would interpret it, if I understand that correctly. All right. Okay, let's call that number x. Okay. Now on that number, I run an algorithm which computes this quantity. This is called the modular exponentiation procedure. All right. Remember my number a, that was part of my input, and the number n, that was the other part of my input, the number that I'm really interested in factorizing. I compute a to the power x. You know, x is the number currently written in my universe, in my memory device, modulo n. And I am able to do this computation quickly and according to the laws of quantum physics. I mean, without showing it to anyone, you know, without my computer interacting with the outside world, with no like thermodynamic loss occurring or anything, right? Computers can do, quantum computers can do all calculations that classical computers are already known to do. And this is a calculation that people have known for a long time, that classical computers can do efficiently. So we are now making our quantum computer make this computation. You know, a number x is written in the memory device. Please quickly compute a to the x mod n, right? And this is a good algorithm, but it's like not hugely exciting. At the end, another place in your computer which stores the result of this computation contains this number, whatever is the result of this number. Now we observe that result register. We observe that number, the result, the whatever a to the x mod n has turned out to be, and like has been placed in the result register of our computer. I observe it. Okay, that's the first time I'm observing something in this computation. Remember, when you observe something in quantum computation, you know, sort of the parallel worlds separate from each other. Now it is no longer possible for me to interact even through strange quantum things with the other parallel worlds in which another number y has been observed, right? Now I am only in a superposition with only the other parallel worlds in which this number y has been observed. So now if I observe my original memory, right, which originally contained all numbers from 0 to m, I would now only have a chance of observing the numbers which, when given as input to the modular exponentiation procedure, would result in y, the number that I observed, right? I lost contact with all the other worlds containing all the other kinds of x's. I now only have these kinds of x's superposed, right, in my memory device. And if somebody now listed the numbers that have a potential of being observed in my memory, they would not be all numbers from 0 to m. They would only be for some randomly selected unimportant x0, some number specific to our world, that number plus r, that number plus 2r, that number plus 3r, you see what's going on? Now I am only have a chance of seeing these numbers if I observe my memory device. All right? Suddenly, the number r that I was interested in from the beginning, that's the number r that I want to know, right? This is the r that we are looking for, the order that we are looking for, has somehow entered the picture, all right? Why is exactly these numbers left in my superposition? Because of the way r is defined. A to the r is equal to 1 modulo n. This follows in like one step from that definition. Okay, so if you think about it, in my memory device right now, which I am not observing, you know, if I wanted to observe it right now, I would only have an equal chance of observing one of these numbers, not the whole thing, not everything from 0 up to n, but only these numbers, which are like are separated from each other, right? However, observing one of them like wouldn't give me a big deal of information about r, right? So I don't want to observe it right now, but I just want to point out to the nice feature of this situation now currently in my memory. If somebody made a list of the amplitudes, I mean the weights, which are associated with the probabilities of being observed, of all the numbers from 0 to m in our memory device right now, you know, most of those chances are now 0, you know, because those numbers have dropped away from our original list, but only some of them are non-zero with the equal values, all right? And those in that list are equally separated from each other. They are equal distance from each other. I mean, you have a number and then many zeros, exactly r positions later, you have the same number again, and then many zeros, exactly r positions later, you have a number again, exactly r positions later, you have that same number again. It's a very interesting situation now. The list of weights of the numbers that are left in my register, in my memory device, is now what the mathematicians call a periodic sequence. And now the genius part, or like yet another genius part of Shor's algorithm is coming. So I have a periodic sequence now, right? And there is something called the Fourier transform that like mathematicians have been using for, I don't know, a few centuries, I guess, which does an interesting thing. If you give to it as input a list, which is a periodic sequence like the one that we just saw, right? The Fourier transform, or like an algorithm which was, I think, invented in the 1940s or 50s called the fast Fourier transform, like a fast version of doing that job, takes a list like that, and if the list is in a periodic sequence as the one that we just saw, it does some interesting thing to it and produces a related list. Okay, details coming soon. But that algorithm has to take the entire sequence as input. We have no way of like listing our sequence, as I told you, right? Our sequence is too long, and also we don't see it. It's just hidden as the amplitudes, as the like weights, probabilities of being observed of some numbers that are sitting on top of each other, or maybe side by side each other in parallel worlds corresponding to our memory device, right? So Shor invented an algorithm, like adapted the fast Fourier transform algorithm to quantum computation, requiring like loads of genius, right? And he poured lots of genius onto this original algorithm, and he made a quantum algorithm essentially doing that transformation on this list of numbers that I have been talking about. All right? That's like the biggest contribution, biggest piece of genius in the algorithm. And, you know, I cannot tell you how this is happening, but I can give you an idea. This is like the very, very heart of the algorithm. This is where the real quantumness of everything is happening. This is where like the remaining parallel branches that we have are interacting with each other, and some of them are canceling each other. Some of them are reinforcing each other. Let me try to give you an example about how, let me try to give you an intuition about how this may be happening. Remember the Hadamard gate? So I showed you this. If you start with a 0, whoop, one step later, you have an equal superposition of 0 and 1. Okay? If you start with a 1 in the Hadamard gate, maybe some of you are already familiar with this. Once again, you have an equal probability superposition of 0 and 1, but it's not an equal amplitude superposition. Interestingly, it introduces the negative sign to the amplitude of the value 1. All right, that's how the Hadamard gate works. Now, remember that, let me do this 0 thing again, boom. At the beginning of Shor's algorithm, we had our bits in state 0, and then we did Hadamards to them. So now, if somebody observes this, he will see 0 with equal probability with 1, right? So that was the thing that happened to our bits at the very beginning of our algorithm. Then we are doing in this stage 3, the Fourier transform. The Fourier transform is like difficult to visualize here, but I can give you the following idea. Hadamard is a very, very simple, like basic kind of Fourier transform. So what happens if I do another Hadamard to this single bit that I have right now? It will, I'm just showing what happens to the 0 part in my single bit register and to the 1 part in my single bit register. So what would be the final superposition after like that second round of Hadamard? You see that the amplitude of 1 is now 0 because the +1/2 amplitude coming from the left branch and the -1/2 amplitude coming from the right branch are amazingly canceling each other out. So something very unexpected really is happening. Something which cannot happen in classical computation is happening. Parallel computational branches are interacting with each other, and some of them are canceling each other out. And the Fourier transform corresponds to a like very, very advanced like Hadamard transform on steroids or something like that, right? So it requires a lot of genius and additional gates to implement, but that's what's happening. As a result of this wonderfulness, the superposition that we had, right? Remember, before this stage, we had this kind of numbers that had a chance of being observed in our memory. Then Shor's genius invents the quantum Fourier transform, which runs in polynomial time, whoomp. And after the quantum Fourier transform, the list of numbers which have a chance of being observed has been transformed into this kind of list, okay? With significant probability. Okay, and once again, I'm saying it's not probability 1, but it's like more than 0.4. That's enough for a Las Vegas algorithm. If you observe your memory right now, you will see one of those numbers in which R, the number that we are looking for, is now in the denominator. All right? So you will see with equal probability either 0, this won't help you, or m over r, or 2m over r, or 3m over r. Remember the m was the big number that we selected at the beginning. Now the our memory device, which we still have not observed, if somebody observes it, will give one of those numbers with equal probability as a result of the Fourier transform done on its previous state. And now we come to the final part of Shor's algorithm. All right, this is what our memory device is containing right now. Finally, we observe it. All right, finally, we read our memory device. From the beginning of the algorithm, we had refrained from observing it in order to keep the quantum magic from being disrupted. But finally, we are ready to observe it. So when I observe it, and I observe the number that I observe a number and call it J, right? What will the number J be like? Well, it will be some integer, which is very close, because that's what I'm telling you, to an integer multiple of m over r, right? Now that I have observed it, I now have no use with my quantum computer. All the quantumness has been lost now because I have observed my quantum computer in all its detail. And the rest of the algorithm is just a classical algorithm. You can drop the quantum computer and just do the rest classically using your classical normal laptop. All right? With this number J, this is a little bit technical, but essentially, you just observe the number J, which is equal to some number K times M over R. If you divide both sides by M, you have a fraction, which is J over M. You both know the numerator and denominator. And you also have a guarantee that it is close to some number over R for some randomly selected number K. Your copies in other universes are now seeing some number corresponding to some other K, all right? And with reasonable probability, so like a reasonable proportion of your copies in all the universes, have it that this fraction K over R is in lowest terms. I mean, it doesn't cancel any further. And so we know several things. We know the number that we just observed. We know the number M that we started with. We have a guarantee that J over M is very close to K over R, right? We don't know what K is. We don't know what R is. And we also know from number theory that R can be at most N. Okay, sorry, but that's what we know. And if you know all those things, once again, Peter Shor was a knowledgeable mathematician, and he knew that if you know all those things, then there exists a pretty old classical algorithm into which you can feed in all this stuff, and it gives you R. Yes, you run that algorithm efficiently, and in the end, you get R. That's Shor's algorithm. Thank you very much. Now, today's quantum computers, as you know, are currently very small. All right. So in order for Shor's algorithm to break RSA encryption and ruin the lives of bankers and so on, we don't have big quantum computers yet. But I guess we will have them sooner or later. All right. And since its invention, Shor's algorithm has been what they call like the killer app of quantum computation, right? I mean, it makes quantum computation an important thing, important area to work at. Anyway, Scott Aronson. He has been your guest in this series of webinars a few times, I believe. So here is something that he says frequently that I like very much. So quantum computers don't just examine all possibilities parallelly and ignore the wrong answers and find the right answer. So this is just simplifying the story too much. All right, we saw what Shor was doing. Okay, most of the job was not done by the quantum computer, but it was done by the genius of Peter Shor, right? So he found this incredibly clever connection between algorithms, and he invented things when they didn't exist and so on. And he was able to like formulate this difficult problem as a problem that is easy for quantum computers. I think he should really get a Nobel Prize. And that's what I will be saying for today. Thank you very much.
So thank you for this wonderful presentation. I think it was one of the best introductions to Shor's algorithm. Every time I listen to it, I'm learning something new about Shor. So again, like, thank you for coming, and thank you for the presentation. Now I will share my screen to ask you some questions like posed by our guests. Also, like, you can still put your questions in the chat in Zoom and also in YouTube to the comments. So like, we have some general questions and also some questions about Shor. The first question is from us. Like, among the quantum algorithms proposed in the last decade, which ones do you find more promising or exciting, like, other than Shor?
Okay, I don't know if it was proposed in the last decade. You know, I am so old and I only remember 2 decades ago and so on. But I think the most amazing and most exciting quantum algorithm that I have seen, you know, apart from Shor is just like a beautiful diamond and so on, is the adiabatic search algorithm, right? I mean, does it work? What are the proofs? And even the people who invented it are not sure whether what kind of runtime it has and so on. It is so full of mysteries, and it is really so exciting from a scientific point of view. You know, you invent an algorithm and you don't know how fast it runs. And you know, Michael Sipser was, I mean, in the original paper about that algorithm, you know, Michael Sipser, the famous theoretical computer scientist, was one of the authors. And I believe there was a sentence like, you know, our mathematical abilities are not enough to analyze the rest of this algorithm in the first version of that paper, right? That's just a wonderful thing to say for such a great mathematician, for all those authors who are all great mathematicians. That's the most exciting thing, in my opinion.
Okay, thank you. Like, I agree, it's like full of mysteries right now, and there are like lots of things to explore in that area. Now, there are some questions about the factoring algorithm. The first one is about adiabatic quantum factorization. And like, so what's your opinion about adiabatic quantum factorization, where factoring problem is mapped to an optimization problem? This is by from Narendra Haigada from India.
Okay, I hope I'm not saying something wrong here. I mean, you may know more about this than me, but as far as I know, the adiabatic way of doing things has been shown to be equivalent, right, to the usual way of quantum computation. I mean, they can simulate each other and so on. So now the question seems to be, you know, whichever kind of computer currently you have your technology about, right? Whichever approach is currently favored by the technological hardware level that we have, that would be the way to go. But you know, once again, maybe I'm not up to date on this, but I haven't heard of like any adiabatic quantum factorization algorithm factoring a number like larger than 100 or something like that. So
I suppose like they did, it was around like 50,000, the number they factored, but I am also not sure. So I might be also wrong, but like for sure it's, they were able to factorize some number which was larger than Shor could do, because like as far as I know, it's like Shor 21, the number factored by Shor, the largest number is 21 currently. So I suppose it's larger compared to Shor, but as you said, this is like about hardware. Right now, the computers, quantum computers, which are working according to this adiabatic quantum computing principle, they are like larger in size compared to other ones. And like, so like that's the reason behind, I think.
Yeah, and maybe, I really don't know, but maybe they don't have the theoretical guarantees about whether their algorithm will work all the time or you know, with some constant probability and so on. But really, I'm not a good person to ask about these things.
Another question, would implementing Shor's algorithm for some large number constitute a definite proof for quantum advantage or supremacy? Asked by Mauricio from France.
It depends on what you mean by definite proof. You know, of course, if a quantum computer is able to factorize such a large number, then for the 99% of world's population, it will be proof that quantum computers are now doing something amazingly important. Like every reasonable person will, of course, accept this. But the remaining 1% are the mathematicians and the theoretical computer scientists. And they may still say, you know, you haven't yet proven that a classical algorithm for doing this quickly doesn't exist. Maybe somebody will invent a classical algorithm just like those Indian mathematicians did, right, after so many thousands of years for primality, right? And then if somebody invents a classical polynomial time algorithm for factorization tomorrow, suddenly that idea that quantum supremacy is there will go away.
So like the first time I heard about this quantum supremacy term, like I said, but okay, like there is no proof. So as you said, like as a theoretical computer scientist, it kind of disturbs you. Another question is about like different ways of computation, such as chemical or biological. Are there any alternative to Shor's algorithm using like chemical or biological computing? This is from Ege from Turkey.
Yeah, once again, I mean, I may not be too up to date on this, but when you say biological computing, I'm immediately reminded about Edelman's algorithm about those test tubes and DNAs, and he's solving what, the Hamiltonian path problem or something like the traveling salesman problem on test tubes, while the molecules representing the different roads between adjacent cities and so on. Okay, I don't think it's fair to compare Shor's algorithm or like quantum computation with that kind of thing. The advantage of that kind of thing, if I understand correctly, comes from the fact that there are so many classical processors working parallelly, all right? If like every molecule is thought to be a processor, then in a test tube there are, you know, so many billions of processors. Okay, if you are able to do factorization with this, wonderful. I don't know if somebody has come up with a biological algorithm for factorization, though. It seems to be difficult. Of course, it is beautiful to nowadays that everybody is thinking about, you know, all those different sciences, you know, chemical computing, I don't know, computing with water bottles or whatever. The connection of computing to various physical things and other sciences and people thinking of algorithms in that context is a wonderful thing. I wish this existed when I was a student.
Thank you. Another question is about security. So when will be the factoring power of quantum computing a risk on current system security? This is by Yusuf from Egypt.
Oh, I don't know. You know, the question is, you know, right, when will it become serious, right?
Yeah.
Okay, you have to ask the hardware people. Depends on hardware, right?
Okay. So let me move. Now we have some general questions. This is from Nevzat. Do you believe quantum mechanics will be revealed to be related to consciousness or free will someday?
I think it is related to everything in some way, of course, right? Since every everybody is made up of quantum particles, definitely at some level, all those things are made up of quantum things. But of course, the question is, does it have to do with the strictly quantum properties of physics? I mean, without superposition, consciousness cannot exist or something like that. So I am a conservative in those things. I think that the brain as a classical computer, which has a representation of itself, right? Can be smart enough to for things like consciousness and free will to emerge. That has been my view once again for like 2 or 3 decades.
Okay, thank you. Would you offer some good entry or beginner level sources or methods to help better understanding or applying quantum computing technology?
Islam would offer things like that to you because that's what they are doing very, very successfully.
So yes, like we are organizing workshops, both like introductory workshops, bronze. Now we have some intermediate level workshop, Q Silver, in which we go through the details of Shor's algorithm, like make the real implementation by quantum programming. So if you're interested, so please join our workshops. And like there's a question about artificial intelligence in general. Could you share your thoughts, advices to teachers for AI for K-12 as a guidance? This is from Beyazıt from Turkey.
The good question. There should be some sort of kid-friendly AI course, or concepts of artificial intelligence and computers and passwords and stuff like that course, I believe. And artificial intelligence, some artificial intelligence concepts are really actually important philosophical concepts that every educated person should learn as early as possible anyway. But at that level, I think teachers would do well to give some reading material or some discussion material to kids so that they can talk about those things. There are like several nice documentaries on Netflix about possible problems that arise from the AI bias problem and so on. This should be part of your agenda, I think.
Thank you very much. Now I will move on to the questions that were asked in Zoom and YouTube. Now the first question is, Shor's algorithm is a hybrid algorithm where part of it is still classical. My question is, can we solve the classical part on a quantum computer? For example, the continued fraction expansion part, and will there be any benefits of solving this classical part on a quantum computer? So this is from Ahmet Yunus.
Yeah, the current understanding is that building a quantum computer is so much more difficult than building a classical computer. So for practical reasons, we would be interested in like just doing the absolutely quantum critical things on the quantum part, and then all the other things on the classical part for like economic reasons, really. There is a famous theorem which says that everything that a classical computer can do can also be done, right, using a quantum computer. So no problem about that. Although, I mean, in the near future, or I think in the far future, people won't have a fully quantum computer as their laptops because it would require their rooms to be minus 200 degrees Celsius or something like that, I guess.
Another question. Will Shor's algorithm end our cryptography system? If so, what can we use instead? This is from Gökalp.
Yes, it will kill the use of security protocols which assume that factorization is a difficult thing. But it seems that there are other security protocols which are not based on that assumption. So something has to change. And the critical thing about, I mean, if you are a state or if you are a bank who uses cryptography for their everyday work, right? I mean, just doing that change cannot happen in one day. All right, so you have to sort of think, when will this happen? When will this be required? If it will be required, I don't know, 10 years from now, if I start now, will my systems be ready, smoothly adapted to this new protocols 10 years from now? You have to sort of think about that.
There was also an answer by Ilyas Savas, so like you can check post-quantum cryptography if you're interested. And I think this is our final question. Yes. Did Peter Shor use the classical computer to make his algorithm?
I don't think so. I think he used, I mean, I've never spoken to him about this, but I think he used a lot of paper and pen.
Okay, then I think those are all the questions. Let me check it again. Okay. And like there's a comment from Abu, he's saying his brain is a classical computer. So yes, if you think it like that, then yes.
But I think in his paper, there are some like numerical experiments about, you know, with this probability, this would happen. But I think during the like creation phase, he used whatever creative powers he had in his brain. Yeah.
So I would like to thank to our participants for joining, and finally I want to like thank Cem Say. Like it was, I was really proud being here. As Abuzer mentioned, both of us are like students of Cem Say. Therefore, like I'm really happy to host this meeting. So thanks again for coming and giving this like excellent talk. Abuzer, do you want to add anything?
No, just thank you, and hope to see you again.
Thank you very much for the invitation. I love you guys.